Welcome. My name is Tutekin. I am a postdoc researcher at INRIA. In this video, I will present our joint work with Emmanuel Vincent and Denis Jouvet. This work was a part of the Comprise project, which was supported by the European Union's Horizon program. In this work, we propose an acoustic model adaptation to reduce the negative effect of accented speech. Here is the outline of this video. I first start with a brief introduction and motivation for our work, then I will describe the essential components of our methodology. Later on, I will present some experimental results on top of that. This presentation will conclude with final remarks and future directions. Let me start with the motivation and our problem definition. Voice interfaces are widely used for daily tasks such as booking tickets, setting up calendar items, or finding restaurants, and even for some other applications like education or healthcare. Although they achieve success, automatic speech recognition systems still perform poorly for speakers whose characteristics don't match those of the training speakers. Accent can be considered as one of the most important factors of this mismatch. Most speakers exhibit a wide variety of accents, usually influenced by their native language or their region. Therefore, current ASR models, trained on native speech, often experience a dramatic loss of accuracy for speakers with strong accents. This affects the overall performance and inclusiveness of voice interfaces. Eventually, we need to treat many different types of people fairly and provide them a decent ASR quality. When we look at the previous studies on this research, we see that main efforts are addressing accent and other factors of speaker variability and focused on data transformation-based methods. For Gaussian mixture model-based traditional models, speaker adaptation has proven to be effective for many years. Despite of their superior generalization ability, deep neural network acoustic models also suffer from speaker mismatch. A simple approach is to retrain the entire DNN using a regularized objective. Another work augments speaker-independent DNN by some speaker-dependent layers or activation functions. Those are trained over adaptation data. These methods are prone to overfitting and induce a large computational overhead at test time. Hence, the most popular approach today is to augment the DNN input features with I-vectors or auxiliary features which embed speaker information and can be quickly computed at test time. By contrast with these speaker adaptation methods, research targeted to non-native or accented ASR is relatively scarce. Early studies focused on adapting the parameters of GMM-HMM acoustic models trained on native speech by maximum likelihood linear regression. Methods that train a specific model for each accent have also been investigated. A unified model is trained on a limited number of accents and then adapted to any accent using grapheme-based acoustic models. Although these approaches perform well, a separate model per accent may introduce computational and storage costs. This calls for multi-accent methods able to recognize non-native or accented speech using a single model. In this work, we propose to compute X-vector-like accent embeddings and use them as additional inputs to an acoustic model in order to improve the recognition of multi-accent data comprising native, non-native, and accented speech. Our model is based on a multi-layer time-delay neural network and trained to identify several accents from variable length segments. This method can adapt on the fly to a non-native or accented test utterance. The embedding DNN requires accented data with accent labels for training, but this data doesn't need to be transcribed. However, the training data for the acoustic model must be transcribed, but it doesn't need to be accented. The details of our model can be seen here. The TDNN-based architecture can classify patterns with shift invariance and can model context at each layer of the network. The lower TDNN layers operate at the frame level. Their outputs are summarized by a statistical pooling layer, and they are followed by some upper layers at the segment level with a softmax output layer. Pooling operation accepts the final frame level layer as input and calculates the mean as well as the second order statistics and the standard deviation. The statistical pooling layer and the upper layers are key in the performance of X vectors. Segment layer embeddings are extracted from the last hidden layer. We finally train the network to classify accent using a multi-class closed entropy objective. In this work, we utilize three approaches for acoustic model training. The first approach is accent unaware scheme, where we only use transcribed native English samples. So we can consider the supervised training as a baseline model. Independently from on-the-fly adaptation, any non-native or accented speech data available at the training time can also be leveraged for acoustic model training. Due to the cost of transcribing large amounts of non-native speech, we assume that this data is untranscribed. This situation is addressed by a semi-supervised learning at the second approach. The seed model is trained on transcribed native samples, and the final acoustic model is trained on both transcribed native and untranscribed samples, covering 1 hour of adaptation data per accent. Lastly, we employ a fully supervised scheme where the training is performed on transcribed native and transcribed accented data. So we can consider this model as top-line as well. We evaluate our methods on native, non-native, and accented speech. For the native and non-native data, we use the wormable corpus, which contains spontaneous speech from human meeting scheduling dialogues. In wormable, we selected American English dialogues as native data and English dialogues from German speakers as non-native data. We also gathered British, Indian, and Australian non-professional accented speech recordings from VoxForge. We created training, test, and adaptation sets with disjoint speakers as shown the table here. Non-native and accented datasets are much smaller than native ones, which is a common setting in a multi-dialect speech recognition. In total, we have 235 native speakers where we use their samples during training. The numbers in parentheses refer to duration in hours. During the evaluation, we use 25 speakers for each group of speakers. For the adaptation data, we use 1 hour speech and 25 speakers per each group. As an acoustic model, we use Caldi's chain models which take 40 mL frequency capsular coefficients over 25 millisecond frames with 10 milliseconds stride as input. Training relies on the supervised or semi-supervised LFMMI criterion. For decoding, we use a 3-gram language model trained over the native English data from wormable corpus with a lexicon consisting of around 7,000 unique words. The embedding network is trained on the utterances of all native and accented speakers in wormable and VoxForge, excluding those in the test set for the acoustic model. A 512-dimensional accent embedding is used over half-second frames. We evaluate 9 different acoustic models on native, non-native, and accented data. On the first row, we present an accent-unaware model trained on transcribed native English speech only. The higher errors observed on accented data is notably due to the higher language model perplexity of VoxForge. Similarly, in second and third row, we used I-vector and X-vector embeddings respectively. For non-native and accented samples, we observed better characteristics over X-vector embedding as well as I-vectors. The next row shows the proposed embedding-based adaptation methods. Compared with the first one, we observe relative error improvements of all data groups. These improvements are remarkable since accent embeddings has been trained on native data only. Next model implements the proposed semi-supervised training method on top of the previous row. Despite the small amount of the adaptation data, this model achieves a relative error improvement compared to previous case. For comparison, we also evaluate fully supervised top lines. Sixth model is a supervised model trained on both the native training data and the non-native and extended adaptation data, assuming that the latter have been fully transcribed. The last one is also a supervised model, which exploits accent embeddings in addition. Note that no embedding model performs comparably and sometimes worse than extending model. This means that our two combined unsupervised model adaptation techniques manage to close the gap and achieve the same performance as a standard fully supervised approach. Interestingly, also, the last experiment appears significantly better than no embedding case, indicating that accent embedding based adaptation provides some benefit in the supervised setting too. In the previous table, we observed that the proposed accent embeddings outperform I vectors and X vectors. This means that internal representations play an important role in adapting to multiple accents. This can be understood by visualizing the embeddings using T-SNE in this figure. Our proposed embeddings tend to be clustered according to the accent, which shows that they are indeed able to catch some accent-specific aspects. To further analyze the impact of accent embeddings, we compare the error reduction achieved for various groups of speakers from easy to hard to recognize ones. To do so, the test speakers for each accent are divided into 5 groups and sorted by increasing word error rates. The relative error reduction when introducing accent embeddings for native-only models is shown in blue line. Native and extended data combination over accent embeddings is also shown in the red line. We observe improvements across all groups of speakers, and these are larger for harder to recognize speakers. In this paper, we focus on the task of multi-accent speech recognition. We propose a simple but effective acoustic model adaptation which combines X-vector-like accent embeddings and semi-supervised LFMMI training. We show that semi-supervised training brings further improvement, closing the gap with a fully supervised approach without auxiliary embeddings. Our method could be also extended as a fully unsupervised scheme where the extended data used to train the embeddings and the acoustic model can be untranscribed. As future work, we plan to combine the proposed acoustic modeling scheme with language model adaptation. We expect this to benefit non-native ASR since non-native speakers may also use specific language variants. This is the end of my presentation. For more information, please don't forget to visit our website. Thank you.